Assalamu alaikum. We'll start with chapter 1, Physics and Measurement. 1.1, Standards of Length, Mass and Time. To describe natural phenomena, we must make measurements of various aspects of nature. Each measurement is associated with a physical quantity such as the length of the object. The laws of physics are expressed as mathematical relationship among physical quantities that we will introduce and discuss throughout the book. In mechanics, the three fundamental quantities are length, mass, and time. All other quantities in mechanics can be expressed in terms of these three. If we are to report the result of the measurement to someone who wishes to reproduce this measurement, a standard must be defined. For example, if someone reports that the wall is 2 meters high and a standard unit of length is defined to be 1 meter, we must know that the height of the wall is twice our basic length unit. Whatever is chosen as a standard must be readily accessible and must possess some property that can be measured reliably. Measurement standards used by different people in different places throughout the universe must yield the same result. In addition, standards used for measurements must not change with time. In 1960, an international committee established a set of standards for fundamental quantities of science. It is called the SI, Systeme International, and its fundamental units of length, mass, and time are the meter, kilogram, and seconds, respectively. Other standards of SI fundamental units established by the committee are those for temperature, the Kelvin, electric current, the ampere, luminous intensity, the candela, and the amount of substance, the mole. Length. We can identify length as the distance between two points in space. In 1120, the King of England decreed that the standard of length in his country would be named the yard and would precisely equal to the distance from the tip of his nose to the end of his outstretched arm. Similarly, the original standard for the foot adopted by the French was the length of the royal foot of the King Louis XIV. Neither of these standards is constant in time. When a new king took the throne, length measurements changed. The French standards prevailed until 1799, when the legal standard of length in France became meter, defined as 1/10 millionth of the distance from the equator to the North Pole along one particular longitudinal line that passes through Paris. Notice that this value is Earth-based standard that does not satisfy the requirement that it can be used throughout the universe. Table 1.1 lists approximate values of some measured lengths. You should study this table as well as the next two tables and begin to generate an intuition for what is meant, for example, a length of 20 centimeter, a mass of 100 kilogram, or a time interval of 3.2 into 10 raised to power 7 seconds. Approximate values of some measured lengths. Distance from the Earth to the most remote known quasar, 2.7 into 10 raised to power 26 meters. Distance from the Earth to the most remote normal galaxies, 3 into 10 raised to power 26 meters. Distance from the Earth to the nearest large galaxy, Andromeda, 2 into 10 raised to power 22 meters. Distance from the Sun to the nearest star, Proxima Centauri, 4 into 10 raised to power 16 meters. 1 light year, 9.46 into 10 raised to power 15 meters. Mean orbit radius of the Earth about the Sun, 1.50 into 10 raised to power 11 meters. Mean distance from the Earth to the Moon, 3.84 into 10 raised to power 8 meters. Distance from the equator to the North Pole, 1.00 into 10 raised to power 7 meters. Mean radius of the Earth, 6.37 into 10 raised to power 6 meters. Typical altitude above the surface of a satellite orbiting the Earth, 2 into 10 raised to power 5 meters. Length of a football field, 9.1 into 10 raised to power 1 meters. Length of the housefly, 5 into 10 raised to power minus 3 meters. Size of a smallest dust particles, 10 raised to power minus 4 meters. Size of cells of most living organisms, 10 raised to power minus 5 meter. Diameter of a hydrogen atom, 10 raised to power minus 10 meter. Diameter of atomic nucleus, 10 raised to power minus 14 meter. Diameter of proton, 10 raised to power minus 15 meters. Approximate masses of various objects. Observable universe 10 raised to power 52 kilogram. Milky Way galaxy 10 raised to power 42 kilogram. Sun 1.99 into 10 raised to power 30 kilogram. Earth 5.98 into 10 raised to power 24 kilogram. Moon 7.36 into 10 raised to power 22 kilogram. Shark 10 raised to power 3 kilogram. Human 10 raised to power 2 kilogram, frog 10 raised to power minus 1 kilogram, mosquito 10 raised to power minus 5 kilogram, bacterium 1 into 10 raised to power minus 15 kilogram, hydrogen 1.67 into 10 raised to power minus 27 kilogram, electron 9.11 into 10 raised to power minus 31 kilogram. Approximate values of some time intervals. Age of universe 4 into 10 raised to power 17 second. Age of earth 1.3 into 10 raised to power 17 second. Average age of a college student 6.3 into 10 raised to power 8 second. 1 year 3.2 into 10 raised to power 7 second. 1 day 8.6 into 10 raised to power 4 second. 1 class period 3 into 10 raised to power 3 second. Time interval between normal heartbeats 8 into 10 raised to power minus 1 second. Period of audible sound wave 10 raised to power minus 3 second. Period of typical radio wave 10 raised to power minus 6 second. Period of vibration of an atom in solid 10 raised to power minus 13 second. Period of visible light 10 raised to power minus 15 second. Duration of nuclear collision 10 raised to power minus 22 second. Time interval for light to cross a proton 10 raised to power minus 24 second. As recently as 1960, the length of the meter was defined as the distance between two lines on a specific platinum iridium bar stored under controlled conditions in France. Current requirements of science and technology, however, necessitate more accuracy than that with which the separation between the lines on the bar can be determined. In 1960 and 1970, the meter was defined to be equal to 1650.763 wavelengths of orange-red light emitted from a Krypton 86 lamp. In October 1983, however, meter was redefined as the distance traveled by the light in the vacuum during the time interval of 1 over 299,792,458 seconds. In effect, this latest definition establishes that the speed of light in the vacuum is precisely 299,792,458 meters per second. The definition of meter is valid throughout the universe based on our assumption that the light is same everywhere. The speed of light also allows us to define light year as mentioned in the introductory storyline, the distance that the light travels through empty space in 1 year. Use this definition and the speed of light to verify the length of the light year in meters as given in table 1.1. Mass. We will find that the mass of an object is related to the amount of material that is present in the object or to how much that object resists changes in its motion. Mass is an inherent property of the object and is independent of the object's surroundings and of the method used to measure it. The SI fundamental unit of mass, the kilogram, is defined as the mass of a specific platinum iridium alloy cylinder kept at the International Bureau of Weights and Measures at Sèvres, France. This mass standard was established in 1887 and has not been changed since that time because platinum iridium is an unusually stable alloy. A duplicate of the Sèvres is kept at the National Institute of Standard and Technology in Pittsburgh, Maryland. Table 1.2 lists approximate values of masses of various objects. In Chapter 5, we will discuss the difference between mass and weight. In anticipation of this discussion, let's look again at the approximate equivalence mentioned in the introductory storyline. 1 kilogram is approximately equal to 2.2 lb. It would never be correct to claim that the number of kilograms is equal to the number of pounds because these units represent different variables. A kilogram is a unit of mass while pound is a unit of weight. Time. Before 1967, the standard of time was defined in terms of the mean solar day. A solar day is the time interval between successive appearances of the sun at the highest point it reaches in the sky each day. The fundamental unit of second was defined as 1 over 60 times 1 over 60 times 1 over 24 of a mean solar day. This definition is based on the rotation of one planet, the Earth. Therefore, this motion does not provide a time standard that is universal. In 1967, the second was redefined to take advantage of high precision attainable in a device known as an atomic clock, which measures the vibration of the cesium atom. 1 second is now defined as 9192631770 times the period of the vibration of the radiation from the cesium-133 atom. You should note that we will use the notation time and time interval differently. A time is a description of an instant relative to a reference time. For example, t is equal to 10 seconds refer to an instant 10 seconds after the instant we have identified as t is equal to 0. As another example, a time of 11:30 am means instant 11.5 after our reference time of midnight. On the other hand, time interval refers to duration. He required 30 minutes to finish the task. It is common to hear a time of 30 minutes in this later example, but we will be careful to refer to measurement of duration as time intervals. In addition to fundamental SI units of meter, kilogram, and second, we can also use other units such as millimeters and nanosecond, where the prefix milli and nano denote multipliers of the basic unit based on various power of 10. Prefixes for various power of 10 and their abbreviations are listed in table 1.4. For example, 10 raised to the power minus 3 is equivalent to 1 millimeter and 10 raised to the power 3 correspond to 1 kilometer. Likewise, 1 kilogram is 10 raised to the power 3 grams and 1 megavolt is 10 raised to the power 6 volt. Prefixes for the power of 10, 10 raised to the power minus 24, yocto, 10 raised to the power minus 21, zepto, 10 raised to the power minus 18, otto, 10 raised to the power minus 15, femto, 10 raised to the power minus 12, pico, 10 raised to the power minus 9, nano, 10 raised to the power minus 6, micro, 10 raised to the power minus 3, milli, 10 raised to the power minus 2, centi, 10 raised to the power minus 1, deci, 10 raised to the power 3 kilo, 10 raised to the power 6 mega, 10 raised to the power 9 giga, 10 raised to the power 12 tera, 10 raised to the power 15 peta, 10 raised to the power 18 exa, 10 raised to the power 21 zeta, 10 raised to the power 24 iota. The variables length, mass, and time are examples of fundamental quantities. Most other variables are derived quantities, those that can be expressed as a mathematical combination of fundamental quantities. Common examples are area, a product of two lengths, and speed, a ratio of length to a time interval. Another example of derived quantity is density. The density rho of any substance is defined as its mass per unit volume. Rho is equal to m over v. In terms of fundamental quantities, density is the ratio of mass to the product of three lengths. Aluminium, for example, has a density of 2.70 into 10 raised to the power 3 kilogram per meter cube, and iron has a density of 7.86 into 10 raised to the power 3 kilogram per meter cube. An extreme difference in density can be imagined by thinking about holding a 10 centimeter cube of styrofoam in one hand and a 10 centimeter cube of lead in another.